Can I invite the panel back up front? And open the floor for comments, discussion, questions, and we'll bring mics around.
I'm Bill Levine. I'm from the University of Maryland in College Park. I wonder if someone on the panel or some people on the panel would like to comment on the role of laboratories and experiments in control.
Tom, you said a word or two about experimentation. What's the role of laboratories and experiments in control?
The role of laboratories
In experiments.
Don't you? I'm puzzled. I mean, you do experiments in laboratories? What do you mean, actually?
Experimental. Okay.
In most scientific and engineering areas, if you heard 3 or 4 hours of discussion like this, you would hear the word laboratory and experiment quite often. It was rather striking that it was never mentioned here.
You mentioned.
Well, I mean, I thought what we did was probably, we were doing experiments with these semiconductor problems that we were working on. But I mean, I don't know, it's part of research, I think. I don't know, it depends on the problem, whether you need actual physical experimentation or not. And often I would think these days the experimentation is done with computers and simulations. And so, you know, the physical experimentation may or may not be done, or can be done remotely in, you know, some other part of the world with controls here and so on. But I mean, well, I don't know. That's
I think another aspect of the question is some of the work clearly is targeted to large, complex systems, the smart grid, for example. And it's a little hard to run physical experiments on the smart grid, right? Or on the National Aviation System, right? And so perhaps the panel could talk about that in terms of, I mean, I think there's the issue of more contained experiments. You can do control experiments in automobiles and vehicles and the like. And we didn't hear much about that, but there's also the issue of very large-scale systems where it's hard to actually make physical transformations for experimental purpose in those systems. Comments from the panel? Pravin?
I think following up on what the two Toms said, I'd like to broaden that question of Bill's to empirical work. As when you talk about experiment, you think about controlled experiment in a lab. When we talk about large systems like the electric power grid or the transportation system, it's difficult to do experiments and even more difficult to do controlled experiments. But empirical research and control or optimization-oriented investigation of empirical data, I would say, are important and perhaps the only way we can get to addressing these sort of large systems. The difficulty I've found in both the transportation and the power grid area is getting data, number one, because data are infrequently collected, poorly collected, not collected for scientific investigation. And second, when experiments do take place, that is to say some conscious intervention in traffic or the power system, it's very difficult to disentangle that from the rest of the system because they're open systems, as Ian talked about, and so it requires different techniques to tease out what the impact of the of the experiment is from the rest of the noise in the system. But perhaps, and so typically people resort to simulation to try and reproduce to whatever it was that is empirically observed. But it's a delicate art, I think, and requires experience and judgment and so on, which is unlikely to be found in theorems. But theorems do guide you as to what you should look for. But so perhaps the role of the experiment, or the role of the laboratory, has diminished when we talk about these large-scale systems. But nonetheless, I think the lessons you might learn in the laboratory in terms of being careful as to what data collection means and what noise means and so on may be very valuable. And maybe statistics or dealing with data in some form or another is something that we ought to teach our students and practice much more than, seem to be getting attention from the panel. Larry?
Now, let me just answer that question this way. I mentioned in my talk about this no free lunch theorem, which basically says the following, that average over all possible problems, the performance of any algorithm is the same as any other. You cannot claim that one algorithm works better than another. Now, of course, in real life, we don't encounter all possible problems. There are certain class of problems that's more likely to be encountered by this algorithm than others, so forth. And so to talk about which algorithm is better and so forth really depends on the distribution of the algorithm, of the problems you're going to face. And that's an experimental thing. And you need to test it experimentally to say one algorithm works better than another. And another specific example, I mentioned this topic that occupied my own research for the last 15 years, ordinal optimization. It was discovered one rainy afternoon. I was playing around with a very, very simple model to dealing with the problem of computation intensity in these very complex systems. And from that, all the theory of the ordinal optimization are created long after that initial playing around with a simple experiment, after which I said, oh, gee, this looks interesting. There must be something there. Then all the theory came afterwards, not because I start from a given formulation, a framework, definition, assumptions, theorem, and lemma, and so forth. It was purely playing around with a simple experiment. So.
Yeah, I would like to expand yet further what Praveen did by expanding the two tomes, namely the empirical work is really a must for engineering education, and we have to grab every opportunity that there is. It is not just the undergraduate lab, this lab, that lab, and Tom talk about the research and Praveen about large-scale systems. I will give a couple of examples where indeed, while the shortage of data for large-scale system is a fact, it is also true that there are exceptions, especially if you don't approach physiology but pathology of the systems, and there are exceptions when there are good data. My students benefited from the post-mortem analysis of the old New York blackout that was given to General Electric, and we had a joint project with General Electric. So the question, first of all, how this blackout came about. It was pieced together by various government organizations, EPRI, and other institutions and corporations. And then, was there something that could have been done to prevent it? The story is long, if a certain engineer wasn't asleep and there was 10 minutes difference if they would wake him up, etc. But it was an interesting game for students to go back to the data and replay the whole thing. Now, the most recent blackout, Northeast blackout, was much more complex. It was also the result of some cheating of some corporations and companies. It would have been even more interesting. I know that the data have finally been collected, but I haven't heard of a university, whatever, say General Electric or some other corporation joint project to go to this data. It is really a treasure of data. Likewise, in some other situations, it is good to point out that while we don't have the data of regular operations, there is a government mandate when something goes wrong then the data appear. So this is maybe the way to increase the possibility of empirical work post-mortem, if not in real time.